Hello Year 12s, this is Mr. Lim again, and this is video number 12 in our Redox series. Okay, so we're almost near at the end, let's go. Okay, today we're going to be learning about electroplating and electrorefining, okay, and then just being able to describe them. Okay, so uses of electrolysis. So last video we learned about electrolysis, which is the forcing of electrical energy into chemical potential energy to change things, to force the chemical reactions. Okay, so we are applying it to different situations to force oxidation and reduction to occur for different purposes. Okay, that's what we're doing for refining and electroplating. So electroplating is the coating of a substance with a desired metal, so plating it, and electrorefining is increasing the percentage purity of the metal. So electroplating. The object to be coated is attached to the negative terminal of the thing. So in this case, it's the key. We want to coat the key. All right. In terms, we attach it to the negative terminal of the electrolytic cell, and the electrons are forced to this electrode, and reduction occurs here. So reduction will usually be the metal ion will come here and turn into the metal atoms on the surface of the thing. Okay. The desired metals ions are taken from the solution and reduced on the surface of the object to coat the object. So you're just going to get lots and lots of these things covering it. Okay. To ensure that the concentration of the desired metal ions, which is this thing, don't reduce, so not to say that they're not reduced, but it's to say that they don't go down. That's the concentration of those ions don't go down. All right. And to ensure that it is the only substance reduced on the surface of the object, the anode, which is the other one, is made up of the desired metal. So if you want to put copper on this key, you make copper the anode. And so what happens is that this electrolyte is now copper 2+. And what happens is that, okay, copper gets reduced and is plated on the surface there, copper. All right. But to keep this concentration constant, copper is placed here so that it oxidizes, because here it's losing electrons, or it's forced to lose electrons, right? And so for every one of these coppers that you put on there, another copper is falling off here. Okay, so this anode gets smaller, this cathode gets bigger. All right. The desired metal is forced to oxidize at the anode, and the concentration of the desired metal stays the same. So we said that every ion that is consumed is replaced at the anode. Having the desired metal make up the anode means that the oxidant and reductant form of the desired metal are present. Okay, so the oxidant and the reductant form of the desired metal, so that's copper and copper 2+, are present. And thus these two things will have the smallest difference. So remember, electrolysis, we're expecting on our standard reduction potential table, here's our arrows. We're expecting things to be uphill, yes? So we're expecting something here and here. And we want to pick the one with the lowest difference. Okay? So if instead of it being there and there, it's here and here, this is the oxidant and reductant form. And since that they are on the same line, they will have the lowest difference, effectively of 0. Okay? So that's the concept there, that we are having both of the oxidant and the reductant there, just to make sure that the concentration of the ion stays the same, as well as it's the only thing that is oxidized and reduced. Okay, so let's have a think. Will the color of this solution change over time? Hopefully not. If you've got one copper going on, you're going to have one copper coming off, which means that you're going to have the exact same amount of copper in the solution at any given point in time. All right. Just remember, even though water is actually, so if this was copper here, water would actually be found lower on it. Okay, so even though it's lower on the standard reduction potential table, it's not going to reduce or oxidize, because it's going to look for the lowest difference, which will be where those are the exact same. Okay, all right. So you can generally electroplate stuff not with copper, but instead with more valuable stuff like silver or gold. And in fact, white gold is actually an impure type of gold, which is kind of white, but then they make it super shiny. They plate it with rhodium, which is a super shiny metal. And then when that wears out, you have to get it replated, and then that costs lots of money. So don't buy white gold. Right. So that was electroplating. this is now electrorefining. So electrorefining is increasing the percentage purity of a metal. An impure sample of the metal is connected to the positive end. Okay, so that's the impure sample here. It's connected to the positive end, making it the anode and forcing that metal to oxidize. Okay, so you're forcing all of these things to oxidize off that particular piece of metal, right? So remember, this is impure, so it's going to have copper and a whole bunch of other stuff, and copper is the thing that we're trying to get. Okay, so it's going to have copper, it's going to have zinc, it's going to have iron, it's also going to have silver, gold, and lead. All right, so when you run this at a low enough voltage, what will happen is that these things here, the zinc and the iron, will oxidize because they are more reactive than the copper, right? So it will oxidize as well as the copper. But these things over here, which are less reactive than copper, will not oxidize because you're only giving it a slow voltage. So therefore, you're not giving it enough energy to oxidize these things, to draw away those electrons from those things. Okay, so those will stay in their solid elemental form. And so those will fall off here and then form this anode mud. All right, so because they are less reactive, right, they will stay in their elemental form and form the anode mud. Because these ones here are more reactive than copper, they will also oxidize. All right. So the question is, how come these ones don't oxidize, don't reduce over there? Okay. The more reactive ions here will not reduce because the voltage is too low, supplied is too low to reduce them. Okay, so you only give it a super low amount of energy, and only the copper and the copper ions will oxidize and reduce. Okay, so this is the purer copper cathode. Okay, this is where more copper ions are coated on it because you're forcing it to reduce. Okay, the anode continues to get smaller, right? So yeah, that's why you see there it's kind of falling apart. And the cathode continues to get bigger until you've got no more anode left or you've stopped supplying it with power. Okay, so just a couple of things. This impure copper anode here, that's not super impure. That's actually like 95% pure. But this pure copper is like 99.9% pure. Okay, so this is not the first step in a electrorefining. It's more like the last step to try and just get that last little bit of purity there. Okay, that's that. Let's have a look at some of these questions here. Okay, so these are exam questions. Here you have a electrolytic cell trying to plate that key. Let's go through. 13. Which of the following statements about the cell is correct? Okay, the key becomes the anode when the cell is operating. Okay, so anode is oxidation. Oxidation is loss of electrons, which is what's happening at the positive terminal. So what happens here is that actually this is the cathode, this is the anode. Okay, so we know that that one is not correct, false. Okay, we can just tell that by simply the battery position there from that last video that we watched. The key will gradually lose mass as the electrolysis process continues over an extended period of time. Well, that's not supposed to happen. The key is supposed to gain mass as it gets plated. Okay? And remember, that's reduction occurring here, so more stuff is going to be added to it over time. Okay? The cathode is the copper rod. Okay? That's this one here. Nope, that's the anode because it's connected to the positive terminal. That's false. So therefore, the true statement is the last one. The purpose of the anode is to replenish and maintain a steady supply of cations, which are the positive ions, in the solution. So remember those positive ions, they're going to be coming here and coating this. To replace those positive ions, you need to take them from that anode. So that is correct. Okay, so that is true, so therefore it's D. Okay, let's have a look at the next one. Which of the following statements is false? Okay, so oxidation occurs at the copper electrode. That's the anode. Oxidation occurs there. Yes, it is. So that is a true statement. So that's not correct. The purpose of the battery is to provide a flow of electrons from anode to cathode. That makes sense. The electrons are, in fact, flowing that way. Remember, the positive end pulls those electrons. That's the positive, pulls those electrons in, and then the negative forces those electrons into the key. So that is also a true statement, which makes it also not correct. Okay. Cations move through a solution from the cathode to the anode. Okay? No, they do not. They go actually in the opposite direction, from the anode to the cathode. Remember, cations go to the cathode. So that's a false statement, so that is the correct one. But let's check D. Okay? Reduction occurs at the site where electrons are made available. Okay? So what does it mean by made available? It means that the battery is pushing them out and making them available here. Right, and therefore reduction will occur here because all of these positive ions will gain an electron, and gaining electrons is reduction. So that is also a true statement, so therefore it's not the correct answer. Let's have a look at this one. A group of chemistry students set up an experiment below to replicate the electrolytic refining of copper, obtain some impure blister copper, so impure, as well as a thin piece of pure copper, that's here, and set it up below. Okay, so they want it to go that way. Okay, so explain the chemical principles of an electrolytic cell, something along the lines of changing chemical potential energy, electrical energy into chemical potential energy and causing chemical changes. All right, so let's have a think. On the diagram above, label the anode and cathode, the sign of each electrode, the direction of cation flow, and the direction of electron flow. Okay, so we know that the pure copper needs to have reduction occur here. We need to have reduction occur here. And therefore, this is the oxidation over here. If that's true, therefore, we know that this is the anode and this is the cathode. Okay? If that's true, then we should know that the positive end is the blister copper, as it is pulling electrons from there, and the negative end is on this side, forcing the electrons into that pure copper thing there. Okay, so anode and cathode we've labeled. Sign of each electrode, we did that, positive and negative. Direction of cation flow, so cations are these ones here, so they should be going that way. Okay, and the direction of electron flow also shown there, going that way, also known as clockwise as well. Okay, that's how we think. Just from that information about which one's a pure copper, which one's a blister copper, we should be able to work out what's supposed to occur, and then work out what all the other bits and pieces from it. Okay. So I just wanted to include this. This is from the WACE 2016 exam, and we'll go through WACE questions later on. But this is a question which is worth 10 marks, and it's all about electroplating. Okay, so I want you to recognize that, yes, you may be asked a 10-mark question just for you to tell me everything that you know about a particular topic. It could be electrorefining, like here. It could be electroplating. It could be the lead acid accumulator. It could be electrolytic cells or galvanic cells or the standard reduction potential table or corrosion, which is the next topic, or corrosion prevention. All right? I want you to be prepared and say that, okay, we are going to study this to a high level so that we can regurgitate information, and lots of it, making sure we cover everything. Okay, so just be prepared. You know, it could be on anything. Even in the WACE exam we're talking about, it could be on buffers, titration curves, indicator choices, primary standards, theories of acids and bases, so many different things. So just really keep that in mind when you're studying, that you do need to know these at a high level. Okay, that's it. That's it for the video. Like and subscribe.